Hello everyone, welcome to BADM A724 Quantitative Methods and Business Analytics. This is Lecture 8. I'm your instructor, Dr. Frank Tian Shea. In this lecture, we'll talk about the sampling distributions and estimation, sampling variation, sample means and the central limit theorem, confidence interval for mean with known standard deviation, confidence interval for mean with unknown standard deviations, and also sample size determination. Okay. We talked about the discrete probability distribution in previous lectures, and also continuous probability distribution in previous lectures. Now this time, let's talk about the sampling variations. We know in statistics or in surveys, research, in marketing, in business research, we often have to take a sample. We cannot possibly survey everyone, the whole population, which is too costly, too time-consuming, and impractical. We can only take a sample from the population and use the sample parameter to estimate. For example, we want to find the usage of cell phones, among the population in your city or in a state, South Carolina, for example. We cannot possibly survey everyone in South Carolina or in your city. So what do? We may survey, maybe 200, 500 people, and ask them, give them a questionnaire, ask them about their usage of cell phones, how much time they spend on that every day, or which apps, which website they use, they look at, to visit, etc. So sampling itself, there is a variation in the sampling, and that creates another issue that we need to deal with. Okay? So about sampling variations, sample statistic. Sample statistic itself is a random variable, because we don't know which subjects we will get from the population. So when you sample, there's a chance someone is chosen, someone is not chosen. So the outcome may be different, right? So a sample statistic itself is a random variable whose value depends on which population items happen to be included in the random sample, right? So we know the importance of having a random sample, but which one is going to be, which one is happen to be included is a random variable, right? It's a random variable whose value depends on which one to be included. So that's sample statistics. Okay? Depending on the sample size, the sample statistic could either represent the population well or differ greatly from the population. Of course, when we do our research, we want the sample to be representative of the population, so the results we gain from the sample is meaningful and can be used or generalized over to the population. And if it differs from the population, it's going to be too bad, right? The sampling or your survey, your research is going to be invalid. Okay? The sampling variation can easily be illustrated. Next. Let's consider the 8 random samples of size n equals 5 from a large population of GMAT scores for MBA applicants. And those, most of you probably have taken the GMAT test and had your GMAT scores. I took my GMAT years ago when I was applying for my MBA program, at Georgia State, professional MBA program, and I forgot how much I scored, But let's say, there are many people, there are hundreds of thousands of people taking GMAT, every year, right? GMAT scores every year. And if you take a sample of 5 from a large population, and then depending on which 5 numbers you happen to have chosen, for example, in sample 1, right? The sample 1 is the first person scored 490, and the second person 580, 440, 580, and 430, right? You can do a calculation of the mean, right, which is 504, and that's the first sample. Okay? You take 5 people, 5 samples from the population, and then you take another 5, right? This time someone scored 310. Ooh, that's pretty low, right? And 590 better, and 730, that's pretty good, right? Pretty high, and 710 and 540. You can see that the average for the sample 2, the second sample, is 576. And of course, the mean sample, the sample means for the population, we know is 520. That is from I think the agency is called the Educational Testing Service, ETS, right? They have all the scores for all the hundreds of thousands of people taking. They can calculate the mean, right? So the mean we know is 520, right? Now, then let's look at the third sample, sample 3. You get 500, 450, 510, 570, and 610, right? The average 528. You can do the same for sample 4, 5, 6, 7, 8, okay? If you look at all 8 samples, each having 5 people each, 5 scores each, you can see what is the highest score. I think somewhere it's probably 730 is highest. Okay, 730 is highest among all 40 people here, from 8 samples here. 310, I believe, is the lowest. No, I'm sorry. There's another one. There's a 240. So all you can see the scores are everywhere. From high as 730 to as low as 240. So all over the place, right? If you just take a sample. But if you look at the means however, the means for this sample 1 is 504, sample 2 is 576, sample 3 528, 500, 540, close to 496, close to 500, 564, and 582. You see the variation among the means are much smaller than variation in the raw score, original scores, right? So in other words, the sample means xi bar tend to be close to the population mean of 520. And that's interesting, and that's important, okay? So you can see the sampling variation, also the importance of taking a mean from different samples, which is a much better representation of the true mean of 520, okay? And if you put the score, GMAT scores on the dot plots, remember dot plots, right? That shows, the blue dots are the actual, scores for sample 1, 2, 3, 4, 5, 7, 8. Right? These are blue dots. You can see the above or below the average line. The average line here is the dot line, dash line here. That's the average, 520. And this is sample 3, all the dots, all the scores in sample 3, sample 4, sample 5, etc. Right? And the red bar, that it shows that the sample means, or the red bar here is here, 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 and here. That the sample means have much less variation than the individual sample items. You can see that, right? All right. And there are some terminologies we need to define, right? And estimators and sampling distributions. What is estimator, right? Here is some population. All test takers of GMAT, hundreds of thousands of them worldwide, right? And here's sample estimators, right? For population, we have mu, ETS, Educational Testing Service, has a number, the mu, or the test average score of all the test takers, hundreds of thousands of them. They can also have the sigma, standard deviation, it can be calculated easily, and also pi, the proportions, right? And if they say maybe the proportion of the test takers who are male or female, or or under a certain age group, between certain age group, no. And the sample, we have x bar, that's the mean of sample. We take a sample from the population, right? The mean is x bar, S is standard deviation, P is a proportion, right? An estimator is a statistic derived from a sample to infer the value of population parameter. That's estimator. Estimate is the value of the estimator in a particular sample. Population parameters are represented by Greek letters like mu, sigma, and pi, when the corresponding statistics by Roman letters X, S, and P. Okay? So that's just the terminology, nomenclature we use. So as soon as you see like Greek letters, that's population parameters. As you guys see Roman letters, this the samples. Okay? So examples of estimators, for example, sample mean is an estimator, right? Sample mean, you take a sample, you get its mean, and use this equation to get the formula to get it, and we can use that to estimate per population parameter of mu. Right? Sample proportion, or P, can be used to estimate the population parameter of pi. Sample standard deviation is estimator of population parameter, population standard deviation of sigma. Okay, these are the formulas, equations to calculate those sample estimators. Okay. What's sampling distribution then? Sampling distribution of an estimator is the probability distribution of all possible values the statistic may assume when a random sample of size n is taken. Let me repeat that. Okay, what is sampling distribution? The sampling distribution of an estimator is the probability distribution of all possible values the statistic may assume when a random sample of size n is taken. An estimator is a random variable since samples vary. You never know which items from the population will be chosen as your sample. Okay? So the sampling, there is error here. The sampling error is the theta hat minus theta. Theta hat is the predicted value, and theta hat is true value. Right? Theta could be anything. Could be mean, standard deviation, or proportion. Okay? Bias. Since the expected value was estimated expected value of theta hat may be different from the true value, so there could be bias. So bias is the difference between the expected value of the estimator and the true parameter. Theta is a true parameter, and the expected value of theta hat is from your sample, and then the difference between the two is your bias. Okay? And of course we hope that your bias is as small as possible. Right? An estimator is unbiased only if the expected value of theta hat equals the true value of theta. Okay? On average, an unbiased estimator neither overstates nor understates the true parameter. Right? That's the best case scenario. Okay? Efficiency of sampling, right? Estimators and sampling distributions. Efficiency refers to the variance of the estimator's sampling distribution. A more efficient estimator has smaller variance. If you look at that, you can see when n is 5, the sample size is 5, this is the curve. Flat, low, flat curve here. It's normal distribution though, right? And then when n is 20, the blue line, that's the distribution. Okay? And then when n is 80, this is the normal distribution. You can see as sample size increases, you have a smaller variance. This variance is smaller, it's more efficient. So a consistent estimator converges towards the parameter being estimated as sample size increases, as shown in this graph. Okay? So a larger sample size is preferred. There's an important theorem called the central limit theorem, or CLT for a mean. Okay, what it says here is, let's see, if a random sample of size n is drawn from a population. You take a sample from the population, takes some GMAT scores from the total, all the GMAT scores, right? And with a mean of mu and standard deviation of sigma, that's for the population. The distribution of sample means x bar, approaches a normal distribution with a mean of mu and the standard deviation of sigma equals the sigma of the population divided by n and the square root. Isn't that wonderful? Okay, I say it again. Yeah. If a random sample of size n is drawn from population, you draw a sample from the population. Right? The population has standard deviation of sigma and mean of mu. The distribution of the sample mean x bar, the sample you have, the sample mean you have, will be more and more likely like a normal distribution. And that normal distribution will have a mean of mu just the same as the population, and standard deviation that's smaller than the population. Okay. And if the population is normal, the distribution of the sample mean is normal as well, regardless of sample size. Okay. Now that's the central limit theorem, and it's quite useful, since we can use the normal distribution to make a calculation. Right? Basically, if a population is exactly normal, then the sample means follow a normal distribution. This is population, right? With mu, the mean of mu, and standard deviation of sigma. Right? If you take a sample from that, you have a normal distribution also. We have normal distribution, and the mu is still the same. Hopefully that's the case, right? We find the mu to be the same or same as the normal population, and then the standard deviation is sigma over the square root of n. So make the sigma smaller. Therefore, the curve is narrower, skinnier, and taller. Okay, so that's what the central limit theorem is telling us. Okay. Also, as the sample size n increases, the distribution of sample means narrows in on the population mean of mu. You can see on this here's a mu. If you take a sample of size of 1, just take one sample, take one person at a time, one person's score at a time. This is what you get, the black line. You sample 2, the red one, and get it taller, right? 4, the green one, you get it even taller. And 8, sample size of 8 is tallest, the blue line. Okay. Sample mean narrows on the population mean, so then you have better, more accurate, estimation. Okay. And interestingly, if the sample is large enough, you take sample is large enough, the sample mean will have approximately a normal distribution, even if your population is not normal. And that's wonderful. Right? If you have normal distribution, the sample distribution is normal, right? But if you take a sample that's large enough, right, the sample means will have a normal distribution, approximate the normal distribution, even if the population is not normal. That's interesting, right? See, if you from a uniform distribution, if you have a uniform distribution, you take a sample from that. If your sample is large enough, the sample means x bar will be like normal distribution. Interesting, right? If you have a triangular population like this, right? If you take a large enough sample, the sample mean will have a normal distribution as well. You have exponential population, sample mean will approximate the normal distribution also. Okay, that's good, right? And here is an illustration of the central limit theorem. Let's say you have a uniform population. Okay, you have uniform population, you take a sample from that. When your sample size is 1, that's what you get. Right? You have a sample size of 1. Right? If you take sample size of 2, you can see it's more and more like a normal distribution, bell curve. Right? If you take sample size of 4, that's what you get. 8, you get something really like a normal distribution. Okay? So that's the beauty of this, central limit theorem in math here. Okay? If you have a skewed population, you take a sample from the skewed population. If you take a sample size of 1, that's what you get. At 2, that's what you get. 4 and 8, you can see it's that gradually approaches a normal distribution. So that's great. That's why we can use normal distribution to solve many problems in business. Okay? So the mu of x bar is mu, and standard deviation is sigma over square root of n. Okay? As you see, that the larger the n, the sample size, the smaller the standard deviation. So the narrower the peak. Okay? Let's take an example here. All possible samples from a uniform population. Look at a uniform population. Okay? Consider a discrete uniform population consisting of the integers 0, 1, 2, 3. Now this is the discrete uniform population, right? Discrete meaning there are only 4 observations, 0, 2, 1, 2, 4. And there is a uniform population because the chances of getting a 0 or 1 or 2 or 3 are all the same. Okay? Now, if we get the sample from that, what do we get? Okay? The population parameters are mu is 1.5. How do you get 1.5? You average over 4, you get 1.5. You can calculate the standard deviation. From that is 1.118. You should be able to do that easily by hand, or by a calculator, or by Excel spreadsheet, or by Excel analytical tools. Okay. Now let's take a sample from that. Remember, this is a population 0, 1, 2, 3. They all have equal chance to be selected. The probability of each point is all 0.25, right? 0.25, 0.25, 0.25, and 0.25 all together is 1.0, right? Unity. Okay? If the population is uniform, yet the distribution of all possible sample mean of size 2 has a peaked triangular shape. You take of all 4 here, 0, 1, 2, 3, right? If you take a sample of 2 randomly, right? If they say take the first 2, 0, 1, right? And then the mean will be 0.5, 0, 1, the mean 0.5, right? If you take these 2, 1 and 2, the mean of these 2 will be what? 1.5. If you take these 2, 2 and 3, the mean will be 2.5, right? What if you take 1 and 3? 1 and 3, these 2, the mean will be 2, etc. You can do that. You can do the over and over and over and take a sample size of 2 and keep doing that. In the end, what you see is the probability distribution for sample size, sample means n equals 2 is actually something like this. You can see it's very much like a normal distribution. Okay. Next, let's look at the confidence interval. What is a confidence interval? Right. Remember, we can use means to estimate, sample means to estimate population. For example, let's say we want to survey cell phone use among all people in South Carolina. Right? We can take a sample of maybe 1,000 people from different cities, Columbia, Aiken, and then we calculate the mean of we can calculate the mean of our samples, and we use that to estimate the population mean. Okay? Let's say we take samples 1,000 people, and we calculate their cell phone use, hours per day, maybe 2 hours, maybe 4 hours a day. Okay? We use that to project to estimate the whole state of South Carolina. Maybe we can do that for the whole country, for the U.S. whole country. But then it's just a point estimate, right? It's just like 2 hours a day on average, or 4 hours a day on average, right? I'm just making it up. I don't know how many hours or how many minutes, right? And maybe spend too much time on there already, right? But that's a point estimate. But we can also use the confidence interval. So instead of saying that people in U.S. spend on average 2.5 hours on cell phones, right? And we can say, we can give a range. You can say maybe 95% of chance people will spend between 2.5 hours, 2 and 3 hours, for example. And that is the concept of confidence interval. A confidence interval for the mean is a range. This is the mean. This is the upper limit. Here's the lower limit. Between upper and lower limit, that's a range. Okay. The confidence interval is the probability that the confidence level contains true population mean. Okay. We are hoping that if you choose a confidence level, that is the probability the confidence interval contains true population mean. A sample mean X is the point estimate of the population mean. Mu is the point estimate. The confidence interval, though, usually expressed as a percentage, is the area under the curve of a sampling distribution. Okay. And what is the confidence interval? The confidence interval for mu with known sigma is this. Right? Is that this is the mu, the population mean, right? And the x bar is the sample mean. You take a sample, and then the confidence interval for mu, when sigma, the standard deviation, is known, is x bar minus z times sigma over n. Sigma is standard deviation of the population, and n is your sample size. And z score is right here, down below. Okay, so it's a minus and plus this. So x bar minus that number right here is this point right here. Right, this is the lower limit. X bar plus that is the upper limit. And this area here in the middle, the white area in the middle, is your confidence interval. Okay, and your confidence interval depends on your confidence level, how confident you want to be. Right? If you want a 90% confidence level, then your z-score is 0.05. 90% meaning you want this area to cover 90% of all the observations. And then if this is 90%, then this is 5% here and 5% here. So the z-score you chose will be z.05 is 1.645. You use a 1.645 as z to calculate the confidence interval. Okay. If you choose confidence level of 90%, you use this z-score 1.645. If you choose 95% confidence level, more confident, you use a larger z-score. You choose 99% confidence level, you choose even larger z-score, 2.576. That means that the confidence interval is wider, is larger, right? Let's look at put that on a different chart. It shows that a higher confidence level leads to a wider confidence interval. Okay, I want you to think about the sentence. Think twice or 3 times. Right? A higher confidence level leads to a wider confidence interval. Here's the 80% confidence level, 90% confidence, 95% confidence, 98% confidence, and 99% confidence. As the confidence level goes up, your confidence interval is higher. Do we see why that's the case? You have to be, if you want to be more confident, you have to enlarge, widen your area, your coverage, in order to include all the possible observations. Right? If you don't want to be that confident, you can choose a smaller, narrower range. Right? So that's the reason. A higher confidence level leads to a wider confidence interval, always. Okay? A greater confidence implies loss of precision. Okay? If you're 99% confident, of course you have to cover a large area, and then you lose some precision. Okay? But the 95% confidence level is most often used. We use that most often. We're happy with 95% confidence. Okay. A confidence interval either does or does not contain mu. Okay. We hope it does, right? But it either does or does not. And the confidence level qualifies the risk. And if you have a confidence level that's too small, you're running a risk, the 20% of chance that the interval does not contain the true population mean. That's be a problem. Then you may want to be more confident, increasing the level. Okay. Out of 100 confidence intervals, approximately 95% would contain mu, while approximately 5% would not contain the mu. Okay. Confidence interval for a mean with unknown sigma. What we just talked about is confidence interval with the standard deviation known standard deviation. But sometimes we don't know the standard deviation of the population, right? In that case, what do? We use student distribution. Use student distribution instead of normal distribution when population is normal, but standard deviation, the sigma, is unknown, and the sample size is small. Okay, this is the equation that for the student distribution confidence interval, and use t, student t, right? And the confidence interval for mu is x bar, the mean, minus that, and as a lower limit, plus that as upper limit. Right? And student t, the score for student t can be found in the book as well, in the appendix. Right? T's distributions are symmetric and shaped like standard normal distribution, are quite similar. Right? The red line here is student t distribution, student t, and the blue is normal, standard normal. You can see they're quite close, especially when sample size is large. They're quite similar, close to each other. Okay? The t distribution dependent on the size of sample. Okay? Also, sometimes in research, in marketing research, business research, we need to determine the sample size. What will be the appropriate sample size? You want to do a survey, a statewide survey or national survey. How many people, how many subjects, how many respondents should you have in your survey? Right? Because the more you have, the larger the sample, the more expensive and time consuming it's going to be. Right? But if it's a too small sample, it may not be representative. So that's the conflict here, right? What do? So how do you determine the sample size? This gives you an idea of estimating the sample size. To estimate the population mean with precision of plus minus e, that's error, sampling error, allowable error, you will need a sample size of n equals z times sigma divided by e and squared. And how do you estimate the sigma, the standard deviation? The first method is you take a preliminary sample. You take a small preliminary sample and use the sample standard deviation in place of s in the sample size formula. Okay, that's you can do. Second method is you assume a uniform population. Estimate the rough upper and lower limit a and b and set s equals this. That's another way for you to estimate sigma. And then with that you can calculate sample size, with a given error. Okay. And a third method, you can assume a normal population, estimate the rough upper and lower limits a and b, and set sigma like that. This assumes normality with most data within 2 standard deviations, so average is 4. So the range is 4 sigma, right? And for method 4 is using Poisson arrivals. In a special case, when mu is a Poisson arrivals, then sigma is simply the square root of mu. You can use that to estimate. Okay, those give you the ways to estimate sigma to determine sample size for me.